So the antipode is defined by gamma of m. I can first write it formally. It is now to have the antipode, you must suppose that the quantum determinant has an inverse. You see, in principle, this is a B algebra. So this is an element of the algebra. It's not guaranteed that every element has an inverse. Now, in the case it has an inverse, then in this case it also has an antipode. If the determinant doesn't have an inverse, there is no antipode, because it's defined through this inverse. So it is defined like delta determinant Q n inverse. So this is an algebraic element. It's not the number -1. And here, now M is ABCD. And then we have to write 4 elements which correspond to, so this of course is gamma of A, gamma of B, gamma of C, gamma of D. And concretely this thing is like this. Gamma of A is D. Gamma of B is minus Q minus 1B. Gamma of C is minus Q C, and this is A. We are finishing in several minutes. In fact, if you forget about the cube, you put Q equal to 1, but sorry. In any case, you can immediately see, even keeping Q formally, this is m to the minus first, because now m of course is only a collection of 4 elements, but if I take this collection of 4 elements and multiply it with this thing, I will obtain 1, the matrix 1. So it is justified, because in a sense when Q is equal to 1, we are getting back into the commutative case, and in that case, that thing is the inverse. So this justifies why I can do this formal operation also here. Why I can do also this operation here. Okay, so actually my time finished, but I only want to mention the following thing, that we have just erased the R matrix. But if I put things, for this two-dimensional case, the R matrix will all the terms will after the first one will disappear. And the R matrix will go to R2 in this case. And this guy will be then equal to Q 1/2, 0, 0, to a matrix 4 by 4, 0, 1, 0, 0, 0, Q 1/2 minus Q minus 1/2, 1, 0. 0, 0, 0, 1. In fact, this maybe I forgot to mention, but the universal R matrix, when Q goes to 1, goes to just unit, of course, in arbitrary dimension, because the sum was going from up to infinity. And also here you can see if Q goes, sorry, here was also Q 1/2. If Q goes to 1, this also goes to the unit. Matrix. Yes, I think that I went over time, but I think that this was important to give also the example of this matrix quantum group. And of course, there is the point about the point about the duality. In a certain sense, the element B corresponds to X plus, The element C corresponds to x minus. And here you have more elements. In fact, in order to have SL2, this is important to say. In fact, until this moment, I was writing what I was writing can be written in this way. So this is the deformation of the general linear group in 2 dimensions. But if I put the determinant Q of n to be equal to 1, then of course I obtain the deformation of SL. In fact, this is what we do in the usual case. In the usual case, if we have 4 generators, we are in GL. If you have 3 generators, we are in SL. And in a certain sense, this is not so easy here because these are operators. But in any case, it's clear that we have 4 generating elements and we have 1 quadratic relation. Then, of course, we do not, then we have only 3 completely independent, and the 4th, in some sense, will be expressed through them. In some sense, because unlike numbers, we cannot just say that 1 is just expressed in this way using this identity 1, but it's a little more complicated. It goes into operator theory and so on. So, thank you.